Today, we will look at a small set of mathematical functions that show up often in statistics. The goal is not to compute them by hand, but to read what they mean for business decisions. We will compare linear, exponential, and log-based relationships, and focus on how slopes and intercepts change meaning across forms. A function is a clear rule that links variables such as y equals f of x. In business terms, x is often the driver, and y is the outcome you care about. The key still is interpretation. Once you see the function type, you can predict how y tends to move as x changes. The graph is not mere decoration. Its shape tells you whether change is steady, accelerating, or flattening. This is why knowing basic function graph shapes can be a helpful skill in the business world. Exponential functions produce curves rather than straight lines. Here the base parameter c strongly affects the behavior, and different bases can create very different shapes. The practical tension is that while curves are realistic, statistical estimation methods prefer linearity to reduce errors. So the question becomes, how do we keep the business story of a curve while using tools built for lines? And the answer lies in using logarithmic transformations. A logarithm is basically the reverse of an exponential relationship. Logs are useful when values fluctuate heavily, or when one variable's scale is much larger than another. In those cases, a log transform can make the pattern look more linear, which supports more stable estimation. The business benefit is interpretability under messier, more volatile data, without pretending the underlying process is perfectly straight. As seen in the graph, changing the scale of the y-axis allows one to view the relationship as a straight line. The key to remember is that if you fail to pay attention to the scale when data is presented, you can unwittingly jump to wrong conclusions and decisions. Always check the scales of any graph to determine if the relationship is linear or curved. We covered this in the earlier video, but a quick revisit can't hurt. In a Lin-Lin relationship, both variables are in their basic form, with no powers or logs on either x or y. The parameter b is the practical takeaway. When x changes by 1 unit, y changes by b units. The intercept a is the expected value of y when x is 0, which is sometimes meaningful and sometimes just a modeling anchor. This format is popular because straight lines are easy to estimate and interpret. The graphs of the two lines indicate how the value of b dictates whether y increases or decreases due to an increase in x. For instance, more work hours might have a negative impact on productivity, but more sales could have a positive impact on revenues. An exponential relationship can be written as a Log-Lin equation. In this situation, we use log value for y, but leave x in a simple linear form. The intersect a is the value of log y when x equals 0. The value of b is particularly interesting here. Unlike linear slopes, b reflects a percentage shift in y as a result of 1 unit change in x. It is critical to avoid interpreting b like a linear slope, because it can lead to wrong business conclusions and decisions. In the graph, notice how the sign of b changes the direction of the curve. A positive b creates upward growth, while a negative b creates exponential decline. Also notice that the curve does not increase at a constant rate. The spacing between values widens or narrows, reflecting compounding behavior, rather than steady linear change. The Lin-Log relationship keeps y in its original scale but transforms x using logs. This shifts interpretation towards diminishing impact of x on y. In the graph, observe how the curve rises quickly at first and then begins to flatten. That visual flattening reflects diminishing impact as x increases. As x grows, the effect of a 1 unit increase becomes smaller. It shows how a percentage change in x changes y by b units. This form is useful when the driver's early changes matter more than later ones. In the world of rapid AI adoption, this type of relationship is seen in how costs change with more usage. The initial cost of investing in AI might seem high, but as the tool gets embedded within the system and processes, the additional costs start becoming smaller. Each additional percentage invested in AI results in lower additional or marginal costs. The log-log relationship is built by log transforming both variables to find a linear estimate of their relationship. The main business advantage lies in the interpretation of the slope, b. It represents the elasticity or response rate of y to a particular rate change in x. That means a 1% change in x corresponds to a b% change in y. which is a clean way to talk about sensitivity. This is particularly helpful when considering price changes in your products or when considering new markets for them. Elasticity allows you to identify what a 1% change in prices is likely to yield in sales, revenue, and profit rates. As you can see in the graph, the biggest thing to be careful about is how values of zeros are interpreted for log-log relationships. Because the logarithm of zero is undefined, those observations cannot be part of a true log-log estimate. However, spreadsheet software may still visually plot zero values, which can visually distort the apparent shape of the relationship. Different function forms answer different business questions, so best depends on the decision you are making. If you need a direct unit change story, use Lin-Lin for simplicity. If you are tracking growth paths, the Log-Lin form would be better. If you are measuring returns or productivity, a Lin-Log relationship is more likely. If you need to estimate responsiveness, Log-Log provides a built-in way to describe sensitivity through elasticity. Across log-based models, the consistent risk is misreading intercepts and slopes as if they were plain linear units. So interpretation discipline matters. Always make it a point to ascertain if your expectation of a relationship is in fact being modeled in your measurements accurately. Start by recognizing the shape. Lines suggest steady change while exponentials suggest curves and compounding behavior. Log transformations are a practical way to handle large fluctuations and to make nonlinear relationships workable with linear estimation methods. Always translate the slope back into business meaning based on the model form, especially for Log-Lin, Lin-Log, and Log-Log relationships. Always label your drivers and outcomes clearly, then pick the function that best matches the decision you are trying to make. Models can provide estimates, but how you interpret and use those values is up to you.